Assalamualaikum. As per in AS syllabus, the certain portion of the chemistry is also involved regarding to the inorganic portion, which consists about 25 to 30% of the total exams. Mostly one question about 20 marks maximum in P2 and 10 MCQs in P1. This section called inorganic chemistry is distributed into three major categories. First, about the introduction and some physical and chemical property of the periodic table elements. Then group 2, second, group 17, third, and nitrogen, sulfur, fourth. So basically four major portion in organic section. First is about periodic table, yes, and second is about group 2, third is about group 7 or 17 called halogens, and fourth is about nitrogen and sulfur. This whole packet or chapters bunch contain lot of things have to be remembered or learned. The first topic is about periodic table. We commonly saw in chemistry the certain arrangement of the element, which is called as a periodic table, regular pattern arrangement of the element on the basis of increasing atomic number. The first definition is about periodicity. What is meant by the periodicity and physical properties of periodicity? So we define periodicity as a reoccurrence of the similar property after each interval of the elements. After each or certain interval of the element, the reoccurrence of the property will be happen. For example, if we consider within periodic table, if we consider within periodic table the element sodium, so we have similar type of properties. We can find similar type of the properties after regular interval. We have the property of sodium, which contain outermost only one electron. So if we move further from the 8 elements, sodium atomic number is 11, 12, 13, and so on. So after 8 element, we have the similar type of the properties which contain potassium. So reoccurrence of the properties after regular interval of the atomic number, reoccurrence of the properties, this is called periodicity. Again, if we consider sodium is a very reactive metal, contain only outermost one electron. For similar behavior of the property which also seen in the potassium, because it also contain only one electron and also becomes very reactive. So reoccurrence of the chemical properties after certain interval or certain number of atomic numbers, which usually 8, 18, 36 in this manner, this is called periodicity. This is the first basic definition, which is called periodicity. And after the discussion of the periodicity, the basic one is we required the different chemical behaviors and related to the atomic numbers, how the different physical behaviors of the element relate to the atomic number. So in periodicity, we don't go to discuss each and every element. We only interested to discuss here 3 elements, which is start from the sodium, magnesium, aluminum, silicon, phosphorus, chlorine, argon. So we discuss the physical property in this period 3 only. The first 5 physical properties which is discussed across the period is atomic radius 1, ionic radius 2, melting point 3rd, conductivity 4. This is the 4 basic behavior, and within the conductivity there's also discussion about the some properties which is discussed in the previous chapter as well, called ionization energy. So altogether the 5 properties, 5 physical behavior: atomic radius, ionic radius, melting point, electric conductivity, and ionization energy, which also discussed in the previous chapter, electrons and atoms. How these properties varies across the period, presenting in the data form or in the graphical form, and then support the arguments why these properties change in this way. For example, if we start from the atomic radius, so first we have to understand what is meant by the atomic radius. So in general, if we define the atomic radius, it is actually the distance between the nucleus and outermost electron within the atom. If a species exists in the element form, if we have a species which exists in the element form, for example, we start from the sodium. So nucleus of sodium towards outermost electron. This distance between the nucleus to outermost electron in the sodium is called atomic radius. Atomic radius usually is very less and measure in the quantity of nanometer or picometer, 10 raised to the power minus 9 or 10 raised to the power minus 12, because it's a very smaller distance, very small distances. So this is a basic definition of the atomic radius, distance from the nucleus to the outermost electron in an atom. But the actual problem is that the electron is very uncertain in position. Nucleus is a dense particle, easily determine, easily find the location, because it is a dense particle, easily reflect the radiation, X-rays or other types of the radiation. So we can easily determine. But the problem is the outermost electron. So outermost electron cannot be easily found. So we change the atomic radius definition in the slightly other way, which is called distance between the two nuclei of the same type. Two nuclei of the same type can be determined and divided by 2. First, measure the distance between the nucleus to nucleus, because distance from nucleus to nucleus is easy to measure. Why easy to measure? Because the nucleus is more confined and more fixed in position. So first you find the distance between the nucleus to nucleus when the atoms are close or brought to each other of the similar type, and then divide it by 2. So ultimately, if we calculate the distance from this point to this point and divide it by half, this value is ultimately the atomic radius. This is a more common use of the definition of the atomic radius as called a covalent radius, because we consider the atom of the same time. So when the atom of the same time, they can attach by each other as a covalent bond as well as a metallic bond as well. So we can also define atomic radius as atomic radius as a metallic radius or van der Waals radius. Metallic radius when the same type of atom brought near to each other due to the force of metallic bond, or same type of atom when brought near to each other by the van der Waals force, or same type of atom brought near to each other by the covalent bond. So half of the distance between the nuclei of the same type divided by 2. This is the basic definition of the atomic radii. If the examiner asks to define atomic radius, we use the definition half of the distance between the two same type of the nuclei. Half of the distance between the two same type of the nuclei. It may be covalent, metallic, or van der Waals. We use the covalent radius if we assume or suppose the nature of bonding between the atom is covalent, like chlorine, Cl2. And we also change the term as a metallic radii if we see that metals are engaged with each other, or converted into the ionic or into the van der Waals radii if we suppose the element exists in the form of the noble gases, which are no type of the bonding is exists. Half of the distance between the same type of the nucleuses is called atomic radii. So how the atomic radii vary? The graphical presentation is here. So we must have to remember graphical presentation, because examiners ask to mark the axis sometime or draw the complete curve. So this is the behavior of the period 3 atomic radii across the period 3 element. So we clearly seen that this is pattern of decreasing pattern in the sum of the neither the linear relation, it is a exponential decrease. So we just require to remember the decrease in atomic radius as we move from the sodium to chlorine. As we move sodium to chlorine, atomic radius decrease. Why atomic radius is decreased? Because proton number is increased. So what effect by increasing proton number is? By increasing proton number, the nuclear charge density increase. We have to define some physical properties across the period 3 elements by justifying the graphical presentation and then the reason behind this trend, justified by trending in graph and then more deeper way as per chemistry. So first, proton number across the period 3 element increases. Argon have the more proton than compared to the chlorine and so on. By increasing the proton number, the nuclear charge density increase. As the nuclear charge density increase, the nucleus more powerfully attract outermost electron. So size of the atoms becomes shrink or smaller. Outermost electron more tightly or more firmly grabs when the proton number increase. Increase in proton number. If we define the trend and reasoning, the first point, trend, atomic radius across the period decreases. First point is atomic radius is decreasing. This is a trend. Why atomic radius is decreased? Because the sodium to argon, the atomic number of proton number increase. As the proton number increase, nuclear charge density also increase. So if the nuclear charge density is increased, nucleus become more energetic, more electrostatically powerful to attract outermost electron, and the size of the atom become shrink. This is a complete description why the atomic radius is decreasing. As you move across the period, proton number increase. By increasing the proton number, nuclear charge density increases. As the nuclear charge density increases, outermost electrons more powerfully attract towards the nucleus, and its size of the atom ultimately shrink. So we also see the effect. The proton number increase, atomic radius decreases in the graphical way. So we have to remember, draw the graph as well as the reasoning behind it. So first is about the atomic radius. The second physical property is called ionic radius. Ionic radius means distance from the nucleus to outermost electron when the element in the ionic state. The same definition from the periodic for the atomic radius and ionic radius, the only difference in the state axis. When the element exists in the atomic state, we use the term atomic radius, or when the term element exists in the ion form, we use the term ionic radius. So trend in the ionic radius is slightly distorted. First decrease, then increase, then decrease. The trend in the atomic ionic radius is decrease, then increase, then decrease. The trend in ionic radius is decrease, then increase, then decrease. Why so? So first, classify the elements from sodium to chlorine, because argon data is not available. Sodium to chlorine, if we classify the elements, so some elements are in metallic side. They are usually involved to lose electron and convert it into the cations. And some elements are in the anionic form, which gains electrons. Within cation, as the magnitude of charge increase, size decreases. Within metal, across the period, magnitude of charge increase, magnitude of positive charge increase, ionic radius decreases. Magnitude of positive charge increase, +1, +2, +3, +4. Magnitude of positive charge increase, ionic radius decrease. Magnitude of negative ion, negative magnitude and negative charge decreases, size also decrease. In case of positive ion, magnitude of charge increase, ionic radius decrease. But in case of the anion, magnitude of charge decrease, ionic radius also decrease. From metal to non-metallic behavior, ionic radius drastically increase. So this graph is divided into 3 sections. First, from metal, sodium +1 to silicon +4, ionic radius decreases as a magnitude of charge increase. The second portion is metal to non-metal behavior, silicon to phosphorus, or silicon ion to phosphorus ion. The ionic radius drastically increase or larger as a magnitude of anion decrease, negative ion decrease, ionic radius also decrease. So if we compare sodium +1, it's contain 11 proton but 10 electron. Similarly, if we move further one, magnesium, which also contain 10 electrons but 12 proton. So what happened in this region? As a magnitude of positive charge increase, so proton number is also increased. If we also saw from the data, magnesium and Sodium. Sodium contain only 11 proton, but magnesium contain 12 proton. As a proton increase, nuclear charge density increase, and more proton more powerfully attract less number of electron. More proton. This is the basic about the ratio. The ratio between the 11 and 10. It is a more likely to tightly or firmly capture. And the more tightly or more firmly capture when that ratio becomes 12 and 10. And oscillarity more far greater when the ratio changes from the 14 to 10 in case of the silicon. Greater number of protons attract more powerfully less number of electron and ionic radius decrease. From here as well, we discuss about the relation between the neutral atom, which is sodium, and sodium ion. If we write the configuration of the sodium ion, as a sodium contain 10 electrons, so 1s2, 2s2, 2p6. This is the outermost configuration of the sodium ion. And for sodium metal, the configuration is remain same rather than the 3s1. So in case of the sodium, the outermost shell is 3s1. 3 shell and S is a subshell. But in case of the sodium ion, the outermost shell is 2p. So we also make a statement. Cation is smaller in size than parent atom. Cation is smaller in size than parent atom. Cation is smaller in size than parent atom. No, this one is more correct way. Sodium parent atom is more greater than sodium ion. Why? Because this one outermost configuration is third shell and S subshell, and here is 2. So third shell is more away compared to the second shell. Parent atom of metal is greater in size radius compared to the ion. Why? Because of the change in shell. As element undergo the losing electron, they usually change in the outermost shell as well. As we see here, the configuration of the sodium is end in the third shell, but in case of the sodium ion end in the second shell. So there is a very large or greater change in the third and second shell. So the atom radius, generally what radius of the parent atom is more larger compared to the parent cation, element cation. In case of the silicon to phosphorus, so move further from this graph, silicon to phosphorus. If we move from the silicon to phosphorus, silicon contain silicon ion and phosphide ion. So again, if we write the configuration of the silicon, is contain 14 proton, but after the losing of 4 electron becomes a 10. And outermost configuration again 1s2, 2s2, and 2p6. So silicon outermost shell is second with 14 proton. But what happens when we move or saw the phosphorus? In case of the phosphorus, more clearly the phosphide, because this one becomes ion. The outermost configuration 1s2, this is a complete configuration, 2s2, 2p6, 3s2, and then 3p6. So outermost shell become third, and here is outermost shell is second. When we move silicon non-metal from metal, if we move metal from the non-metal, there is a greater change in the ionic radius because of the change in the shell. How the shell is changed? Because outermost configuration of metal like silicon is end to the second subshell 2p6. But in case of the phosphide, the outermost configuration 3p6. So third shell is further away from the nucleus, so ionic radius increase. As the magnitude of anion decreases here, magnitude of anion or negative ion decrease, atomic ionic radius also decrease. Here is a opposite behavior. In case of the positive ion, more the positive intensity, more smaller the size. Here is the reverse. Why reverse? Because the increase in the proton, increase in the magnitude of charges here, and ionic radius also increase. But if we make the sense, decrease the charge intensity. decrease the charge intensity or decrease the charge intensity or magnitude of charge, ionic radius of anion is also decreases. Ionic radius of anion also decreases. So what happens if we compare phosphorus and sulfur or phosphide of sulfur? The outermost configuration of phosphide is here. And similarly, in case of the sulfur, the outermost configuration is remains same, which is third or 3p6. But only difference is that phosphorus contain 15 proton and sulfur contain 16 proton. So here is the difference between the 15, or there is actually the attraction between the 15 proton and 18 electrons. And here is the attraction between the 16 proton and 18 electron. If we already state that as the proton number increased, this is because the ratio, what ratio? Proton and electron. As the ratio between the proton and electron is increasing towards more proton side, the attraction will be increased. If this ratio and size decreases ultimately, if this ratio shifted towards the side of the more electrons, so atomic radius or radius in simple way, ionic radius, because we are discussing the ionic radius is increasing. 15 proton more powerfully, 15 proton less powerfully attract 18 electron, while 16 proton more powerfully attract 18 electron, because these differences become narrow compared to this one. And if we move further, in case of the chloride, we have the 17 proton and 18 electron. So this difference is more smaller. As the difference between the proton and electron decreases, the electrostatic attraction impact is more significant. When the electrostatic attraction becomes more significant, the size becomes shrink. So if we conclude all this discussion here, so we first conclude ionic radii, distance from the nucleus to outermost electron in an ion. Ionic radius across the period 3, sodium to silicon decrease, silicon to phosphorus increase, phosphide to chloride decrease. Or in simple way, with as a magnitude of cation increase, ionic radius decrease. As the ion changes from the cation to anion across the period, ionic radius increase. As a magnitude of the anion decrease, ionic radius also decrease. They are the three different behavior, first, second, and third. How this graph further explain? Within the metal, as a magnitude of charge increase. For example, if we compare the magnesium and chlorine, magnesium and aluminum, if case of the magnesium ion and chlorine, aluminum ion, magnesium ion contain 12 proton and 10 electron. And here is a 13 proton and 10 electron. So greater number of proton more powerfully attract. Greater number of proton more powerfully attract less number of electron compared to this behavior when the number of proton is decreased. More proton more powerfully attract less number of electron and ionic radius shrink or decrease. If we move silicon ion to phosphorus ion, ionic radius increase because of change in the shell. This configuration N2p6 and this configuration N3p6. And further, third portion of the graph, as the magnitude of the anion decrease, ionic radius also decrease. So how we justified this statement? Because phosphide contain 15 proton and 18 electron. In case of the sulfur, 16 proton and 18 electron, sulfide. In case of the chloride, 17 proton and 18 electron. All three contain the same number of electron, but the proton number is different. Greater number of proton always attract more powerfully. Greater number of proton, as a proton number increase, or greater number of proton more powerfully attract as same number of electron, because there is no change in the electrons. All contain the same number of electrons, the only change in the proton. More number of protons more powerfully attract. More number of electrons more powerfully attract electrons, so the size decreases or shrink. This is the behavior of the ionic radius. We have to discuss physical pattern or physical properties of the period 3 element across the period 3 element in the periodic table. Atomic radius throughout decreases, ionic radius within metal decrease, metal to non-metal increase, and within non-metal also decrease as the magnitude of charge decreases. There is a one more reasoning why if we compare phosphide with phosphorus, as we compare sodium ion with sodium. So if we compare phosphide with phosphorus, so what is the difference or what is the radius ratio or changing the radius? If we already state that parent atom is greater in size than cation. Similarly, this statement is reversed. Anion is greater in size than parent atom. So how this one is happen? Now again, we move to the electronic configuration. So electronic configuration of phosphorus is outermost shell is 3p2 and 3s2 and 3p3. Is contain 15 electrons and 15 proton. But here this ratio is changes 15 proton because the proton number is same, but electron increases 18. As we already stated that the greater number of proton is a reason to attract the electron. Here is a 15 proton, less number of electron compared to this one. If we compare these two, so less number of electron more powerfully attract to the proton as compared to the more electron attract towards proton. Here is the number of proton is same. So only change in the number of electrons. Greater number of electron less powerfully attract towards the nucleus compared to the less number of electron. Less number of electron more powerfully attract, more number of proton less powerfully, less number of electron more powerfully attract towards the nucleus. So size become reduce or shrink. As the number of electron increase within the same element, within the same nuclear charge density, within the same element, same atom, as the number of electron increase, greater number of electron less powerfully attract to the nucleus, and ultimately the size of the atom increase. So we also made the statement called parent atom is smaller in size than anion. Or in case of the cation, parent atom is greater in size. Here the parent atom or atom is greater in size compared to the cation. And here is the reverse. Parent atom is smaller in size compared to the anion. There are the two physical behavior, atomic and ionic radiuses. The third is the melting point. Melting point across the period 3. The graphical presentation of melting point across the period 3 is this one. So first is again the definition of melting point. Melting point means that when the element changes its state from the solid to liquid at a fixed temperature, and also include the fixed temperature and pressure. Both is considered to be a correct. Melting point is a fixed temperature at atmospheric temperature when the state change from the solid to liquid. The behavior of the melting point is plotted in this way. This pattern is across the silicon is increasing with a not in a regular behavior, and similarly for the non-metal is decreases, and again is for not a particular pattern of the decreasing. If we call the pattern of decreasing, so it's like this one, and for increasing pattern, so it's like this one. So it not actually follow the particular trend, is a slightly random or changing in pattern, both side, metal side and non-metal side. If we go more deeper way, how this is change or this one is relate, this is actually because if we go more deeper way, melting is a physical property, and whenever we discuss about the physical property, we are interested to the attraction between the particles. Means that sodium, magnesium and aluminum, all sodium particle attract with other sodium particle because of the metallic bond. Silicon is a giant covalent structure, is a covalent bond with giant covalent structure, and these remaining four all are the covalent with a simple molecular structure. Bonding metallic structure, giant metallic lattice. Bonding covalent structure, giant molecular lattice. Structure bonding covalent structure, simple molecular. So within the metal, as a number of delocalized electron increase. In case of the sodium is group 1, so outermost 1 electron, outermost 2, outermost 3. As a number of delocalized electron increase, metallic strength also increase. which provide structure to more firmly, more confinedly packed. As a structure becomes more firmly, more tightly, confinedly packed, required more thermal energy to dislocate or further apart, to break into the or basically demolish the attraction between the particles, which is because of the metallic bond. Within the metal, as a metallic electron increase, which is also called sea of electron. So metallic electron increase, the metallic strength, or reverse way, metallic electron increase, metallic strength increase, and particles are more tightly, more firmly packed. And more when the particles become more tightly, more firmly packed, it required more thermal energy. So we saw this trend. This is the trend in case of sodium, magnesium, and aluminum. But we've also found if we follow this trend, so it's likely to this one. But magnesium is rather this position is quite high. The actual chemistry behind is that the existence of the magnesium in geometrical form is quite different from the sodium and aluminum. That's why they are more drastically differ with each other in the boiling. But here within the AS syllabus, we also justified this one. How? The difference of the delocalized electron from the sodium to magnesium is 1:2. 2 is actually double of the 1. But magnesium to aluminum is not actually the double. There is a change in the metallic melting point between magnesium and aluminum, but it's not as same as the sodium to magnesium. I am discussing here that the boiling point magnesium, sodium, magnesium, and aluminum gradually increase because they are more delocalized electron. So a delocalized electron increase, the melting point increases. So this one is a correct, no issue. But the problem is if we move from sodium so if we move from the sodium, magnesium, if we move sodium, magnesium, and aluminum, delocalized electron increases, metallic bond is strengthened, strength becomes stronger, so more tightly packed, more thermal energy required, melting point increases. That's okay, good. So while there is a no significant change if we saw the magnesium to aluminum, the reason is in this AS level, we justified that as the number of electron increase from sodium to magnesium is because actually double. But in case of the magnesium to aluminum, it's not double because the number of valence electron in magnesium is 2 because within group 2 and in aluminum is in group 3. So number of electron from magnesium to aluminum is not drastically increase, drastically or is called double. Either the number of electron increase in double ratio, but there is a no double ratio. The ratio is 3/2 or 1.5. 3/2 or 1.5. So number of valence electron here has become double. So more rise in the melting point, and here the ratio is not become actually double. So the melting point is increased, but not too much. The graph is very slightly is this way. In case of the silicon, the highest melting point across the period 3, because this one is a covalent bond with giant covalent structure. So continuous network of covalent bond make the silicon atom very firmly or tightly packed. Or silicon are covalent bonded with a 4 silicon atom likely to the shape of the tetrahedral. So tightly packed structure due to the continuous network of covalent bond make the silicon particles very firmly or tightly packed. So lot of thermal energy is required to break this attraction. As you move phosphorus, sulfur, and this one, they all exist in the simple molecular form. But the difference is phosphorus naturally exists P4, sulfur exists acid, chlorine exists Cl2, and argon exists in this one, simple atomic form. And we also discussed previously as well, when the structure is simple molecular, the only attraction between the particle is weak van der Waals force of attraction. Weak van der Waals force of attraction is according to the intermolecular forces is induced dipole. So one P4 particle is attracted another P4 particle and a similar another P4 particle with the induced dipole only. Similarly, in case of the acid, sulfur, is also attract with other sulfur particle with induced dipole force. An induced dipole force is depend on the total number of electron. Actually, phosphorus 1 unit contain 15 electron, but phosphorus exists in the P4. So overall electron in the one phosphorus unit is 60. And one similarly for the sulfur, if we count the total number of electron in case of the sulfur. So in case of the sulfur, one sulfur is 16, but sulfur because existence of the sulfur in S8 form, so we have 128 electron per sulfur atom, per sulfur unit because it contain S8 or 128 electron. They all contain this one. Because all particles in phosphorus, silicon, and further move on, they all exist in the simple covalent structure. And the simple covalent structure or simple covalent bond relate to the simple covalent structure and simple covalent bond induced dipole contain induced dipole. And induced dipole strength as the number of electron increases. Induced dipole becomes stronger as the number of electron increase. So phosphorus unit contains 60 electron. Phosphorus unit contains 60 electron. Sulfur unit contain 128. So number of electron, total number of electron between the phosphorus is 60. Sulfur 128. Greater the number of electron, greater the strength. And then chlorine and then argon, because chlorine exists in the Cl2. 17 becomes 34. And for argon is contain argon is 18. So more number of electron, more powerful induced dipole. Just a minute. So as a number of electron increases, the more powerful induced dipole, and strength of the induced dipole means more thermal energy is required to break the bond, and melting point changes as the induced dipole strength change. Stronger the induced dipole in this case, more stronger induced dipole in this case, and then in of the here and then here, because the number of electron increase, induced dipole also increase. So greater induced dipole in case of, here is a more induced or stronger dipole than here. Oh, sorry. This one is a less induced dipole compared to the sulfur because it's contain 128 electron. It's contain 60 electron. It's contain 30 because chlorine is Cl2 form, 34, and here is a 18. So greater the number of electron, more stronger the induced dipole, and higher the melting point. Yes, good. So this one is depend upon, again, this section is break into three categories. First is matter. Metallic bond increase, metallic strength increase, more thermal energy is required. Covalent with a giant covalent radii. Simple molecular structure with induced dipole. And induced dipole is only depend on the total number of electron rather than the other. So total number of electron increase, induced dipole becomes stronger. So sulfur is contain more induced dipole, so more stronger attraction between the sulfur particle and higher the melting point among the all non-metals. The similar pattern is also be justified by electric conductivity as well. The electric conductivity, as we know that the metal is only the region which contain the free delocalized electron. The presence of the delocalized electron is basically the cause of conduction. As a more delocalized electron, more the conduction. So in case of the sodium, magnesium, and aluminum, so in case if we move from the sodium, magnesium, and aluminum, so aluminum contain more delocalized electron and then magnesium and then sodium. So there must be a likely the highest conduction in aluminum because of the more free delocalized electron. While silicon is and other element classified as a non-metal. Their silicon somehow show some metallic behavior, but they are not significantly metal. So they all know delocalized electron, or very few in case of the silicon. So silicon show very little conduction. So greater conduction in case of the sodium, then magnesium, and then aluminum is the highest conduction. And the conductivity, if we draw the conductivity, or conductance versus tier 3 elements, sodium, magnesium, aluminum, silicon, phosphorus, chlorine, sulfur, and chlorine. So in case of the sodium to magnesium to aluminum, this one is increased. And for silicon, there is slightly, and then almost touch to the zero. Almost no conductivity, because they all no free delocalized electron. But in case of the silicon, they are slightly exceptional because of the very few delocalized or free electrons, or called semiconductor. So conduction within metal increase as a delocalized or metallic electron increases. This is the fourth behavior. Atomic radius, ionic radius, atomic radius, ionic radius, melting point, conductivity, and fifth is a ionization pattern, which already discussed in the chapter 2 as well.